So I'm going to talk to you a little bit today about learning healthy models for healthcare. So for some background, I did a PhD in computer science at MIT. So that's kind of my training. And during my PhD, I spent a lot of time sitting in hospitals in the Boston area and looking how doctors practice and trying to make some sort of robust understanding of how machine learning can improve healthcare in different ways. I almost didn't make it here because for those of you who have not been to Toronto, in the major airport there, Pearson, the international airport, you have to clear immigration, US immigration on the Canada side, on the Pearson side. And there were all of the nice, immigration booths, and there were 0 officers at that booth for 2 hours. And when we asked, there's like a mob of angry passengers, like, what's going on? They said, well, they're at the border. And we were like, this is a border. Like, what border are you talking about? They're like, no, the border. So apparently, a lot of our screening officials are at the border, just so you know. So I'm going to start today out with asking you, like, pop quiz, right? Because we don't have coffee in here, so I have you at your weakest. So what we usually consider to be evidence in medicine, right? And these are things that I learned during my PhD because I'm not a medical doctor, right? So the doctors on my thesis committee forced me to learn these things. So randomized control trials are what we believe are the evidence that should be used for determining whether a treatment is effective, right? And if you're thinking from the machine learning or algorithm perspective, you might think, well, these are sort of the gold standard, so maybe we should be optimizing for something like this. So the first pop quiz is, what percentage of treatments that are currently used in hospitals today do you think are based on an RCT? 3%, Cynthia. God, you're killing me. It's 10 to 20%. It's not that bad. It's not that bad. All right. So the follow-up to this is, and these are medical journals, right? This is no computer scientist was harmed in the making of these numbers. Let's take something that did have an RCT. So for asthma, which is very common, right? I think it's 1 in 8 American adults that have it now. They did randomized controlled trials. So they put up a bunch of ads. They had people come in. They looked at inclusion-exclusion criteria, and they tried a bunch of different treatments. And there is now a set of guidelines that we all agree is the gold standard for treating people with asthma. So the question is, what proportion of people today who are being treated would have qualified to be included in those RCTs? It's something lower, right? So unfortunately, in this case, only 6% of asthmatics would have been included, would have qualified to be included. So 94% of people who are currently treated are part of the exclusion criteria. They wouldn't have been allowed to participate. So this should worry you, right? Because I love the name of this paper. It's the external validity of our CTs. To whom do these results apply? We don't actually know, right? So starting from that sadness, why is this important? It's important because human treatment pathways as currently practiced, right? This is not in an RCT setting now. This is George Herbsack a few years ago somehow convinced a bunch of people to pool their sources of medication claims together. So this would be saying, for example, I'm diabetic and I get medication A, and then that's not working so well, so then I get medication B, and then I get medication X. But maybe somebody else gets medication X and stays on that for a while, gets Y, gets A, gets B, gets C, right? So that's your pathway. And so in this data set of 250 million patients across 4 countries and 11 sources, how many people would you assume, what percentage of people would you assume would have a completely unique treatment pathway? Meaning no other patient ever in this data set had the same trajectory of medications. My assumption was it would be small, right? It's not as small as you would like it to be. It's 10% of diabetics, it's 11% of people with depression, and it's 24% of people with hypertension, which means if you ask the question, in an underlying population of 250 million patients, based on my 3-year treatment pathway, what patients are similar to me? Who could I learn from? The answer for a quarter of people with hypertension is nobody. You have 0 nearest neighbors. So if we're starting from there, knowing that RCTs don't apply to everybody, right, by design, And also empirically, human treatment pathways are relatively unique. The question is, maybe there's an opportunity, right? So this is why there is a machine learning for health sort of field, because we think maybe we could use data to understand what's healthy, what works for different populations, what are optimal treatments. And lots of things could be medical data, right? It doesn't just have to be what we traditionally think of as medical records. The ways that you interact with your environment could be medical data because it's about how you are healthy. So, but the problem with working with medical data, with all data, is that bias is already part of the landscape. And importantly for machine learning and health, we know it's part of the clinical landscape. There are many robust studies that have demonstrated that biases in society are reflected in the biases in your healthcare data. This is a well-known thing. And so the question is, how do we interact machine learning with healthcare in a way that respects fairness? And so the ways that we've been talking about this within this sort of sub-community are three ways, right? So there's inequality of access, right? And so this is if you're looking at data, right? Do two people get access to the same resources? Can Mary and Ian see the same category of doctors? There's inequality of treatment. Maybe Mary and Ian can see the same kind of doctors, but Mary gets different treatments than Ian does. And finally, there's inequality of outcome. So this would be Mary and Ian see the same kinds of doctors and get the same kinds of treatments, but they don't work well for Ian, for example, because of existing social determinants. So much of what I've looked at, and this is very new stuff, right? So I don't think there is not a ton of work in this field right now. I think it's growing. Has to do with differences in treatment. And so, for example, we know that patient populations have treatment differences by all of the variables we would not want them to have treatment differences. So race, sex, socioeconomic status. If you can choose something you think that there is a bias in, chances are your data will reflect that. And so the question is, how do we ensure that learning and prediction is fair across those groups where we want it to be fair? So my group in Toronto focuses on creating actionable insights in human health. And so there's three broad categories of research that I target. Today I'm going to talk very briefly about two papers that we've published in the machine learning, health, fairness sort of subspace, and then I'm going to bring up sort of broader future questions. So the first is the very first thing that we looked at during my PhD a long time ago. This is eons ago now. So the question is, it was the first time that I had worked with real hospital data, so about 40,000 patients in the MIMIC3 data set from Beth Israel Deaconess Medical Center ICUs. Can we use the data about an individual, a patient, to predict whether they're going to die in the next 24 hours? So this is important because doctors often have to do backhand or back envelope calculations about acuity. How sick do I think this patient is? There's no actual data. Nobody actually writes those down somewhere in the EHR. And so we're using mortality as a proxy for acuity. And instead of just using labs and vitals, this numerical information that is commonly used, we chose in this early work to use the clinical notes. And we chose to do that because when I was rounding with doctors, I noticed that they did not often look at the labs and vitals with the same frequency that they look at their notes. And so we use a standard, I would say it's now one of the first things people do to process clinical notes method called LDA. We can talk more about that during a break if you're interested, but it's very standard, I think, in many communities now, to model 500,000 notes on about 20,000 patients. And then we use those topics to predict mortality, and we compare them to the standard sort of static measures that were used at the time to predict mortality. And what we found is what you might imagine, which is that the standard sort of baseline models that were used by doctors, right? So these would be things like comorbidity scores, acuity scores, gender, what your admitting diagnosis was. That's the blue line, and its performance, where higher is better, does worse and worse as you spend more time in the hospital, which makes sense. They go stale, right? You score somebody when they come in, and now it's not relevant 24 hours later. But the topics, which are in red, do better and better over time because you're accumulating power, right? You're accumulating information about an individual. And when you combine them in green, that does best of all. So this is all very nice. It's like a pretty result. So that was 5 years ago now. And just last year, at the end of last year, a doctor poked me and said, did you ever check to see how well your models do across different groups? And I said, I included those variables in my model, so of course it's fair. But obviously it's not. So just this year in the AMA Journal of Ethics, we have a follow-up piece that we published showing that, in fact, these state-of-the-art models, and mine in particular, the one that I trained 5 years ago, right, that we had this initial work on, they're not fair. If you define fairness as having equal accuracy between different groups. And so in particular, it's not fair across insurance type, ethnicity, and gender. And so I think the important thing to take away, or that I took away from this experience, is that including race or insurance or gender, whatever variable you've included, which I would say as a machine learning community, we've been conditioned to think of as being the thing to do. You include those things in your model and you're good to go, ship it. It's really not enough, because if you include genomics data as an input modality, that doesn't give you, the same as including race as a variable, all of the different interactions that are going to occur, because race is a social category. It's not a biological truth. And I think within the machine learning community, we don't really think of it that way right now. You include this data in your model, and therefore you think that it must be robust. But that's not actually true. And so briefly, the second thing I want to cover is issues of trust. And so there was this nice paper a year ago in Ontario that looked at whether recent immigrants, so the thing to keep in mind here is, yes, go ahead.
Just a clarification about what you said. So are you saying that your definitions are incorrect of race?
No, it's self-reported race. So as correctly as race.
You're using self-reported.
Yeah, so we're using the self-reported race. It's not enough.
So it's not the issue of not using the variable. It's the issue that that variable is not correctly assigned.
No. We use the variable, and the variable is correctly assigned in the model as an input. But using the variable, even if it's correct, even in your model, is not enough if you're optimizing AUC on a global population. We didn't have, optimize A subject to constraints of these, right? And most of us don't, right? When we train a model, we don't say, and now make sure that insurance types do equally well. So this is the issue. Even when your data is correct, even when it's self-reported, even when you include it, it's not enough.
I have one quick other question.
Yeah.
So is this holding steady, like the same number of notes for patients of different types? Because one could imagine that doctors take different numbers of notes for people in these different groups.
So there are more notes for certain kinds of patients. The issue with looking at note length is specifically in the ICU, there's high turnover. And if you're there longer, so when we looked at differences in the number of notes by length of stay, there wasn't a statistically significant difference. You do often get longer notes in a very specific case that I'll cover later. So the second part of this is, so in Ontario and Canada, we have a single payer system, right? The provinces in Canada are much more independent than states in the US, right? So they have significantly more jurisdiction over what happens within a province. There's sort of a weaker federal government, for better or worse. So in Ontario, a study was done last year where they looked at immigrants, because there's a one big database that just says, who is an immigrant and who isn't, who's a recent immigrant. And they looked at end-of-life care. And so something to keep in mind is end-of-life care is a contentious topic, okay? People are dying. They often want to be as comfortable as possible when they're dying. It is a very sensitive and emotionally loaded time for everybody. And so what they looked at was aggressive end-of-life care. This means in your final days, did you get aggressive treatments that did not change the outcome? You were dying, and yet you spent your final day using aggressive mechanical ventilation and vasopressors, right? So this is the definition that they used, and they found that specifically non-Northern European, Northwestern European immigrants to Ontario got significantly more aggressive end-of-life care than people from Northern and Western European countries, and then long-standing residents in Canada. And so they are very careful in the study, I should say. You should read this to caveat everything they say, as saying, well, we don't know what's going on, we don't know why, we're not saying doctors are bad, et cetera, et cetera. And so we tried replicating this in the MIMIC data set because it's open, right? And so it's something that we would like to examine. And specifically within the American context, we looked at whether African American patients receive longer durations of aggressive treatment at end of life. And they do, so this is just one line query correct. They do receive longer durations of these treatments. And the hypothesis we wanted to test is that could this be a result of mistrust? And the reason this was our hypothesis is the doctors that we spoke with suggested that when they have had end-of-life care discussions in the hospital, often there is this lack of trust specifically with minority patients. They say, doctors have never been sort of trustworthy with me, and so now you're telling me that I'm dying and there's nothing can save me. I don't agree with that. Give me all the treatments. And so what we did is very simple from sort of the methodological point of view. We trained a model to detect mistrust in notes by labeling known mistrust issues in the notes. So non-compliance is a known issue within minority communities. The doctor says, I would like to do A, and you say, no, I will not do A. You AMA yourself, against medical advice yourself. And then autopsy rates have been noted in the epidemiological community as being a marker of mistrust. So a patient dies, and then you say, well, I really want to check that they died from the cause that you say they died from. So I'm going to go relatively quickly through the rest of this so that I have time for the ending matter. So we trained a model using features that we extracted. So we learned based on a subset of labeled examples of mistrust, and this is based on noncompliance and autopsy. And it's looking at things that you might imagine that it would look at. And then we train on a larger set of data to try to say, in patients where we can't look at every single note, but if we label a subset of them and say we know what mistrust and trust looks like in these notes, in this data, we can generalize that to a larger population. And once we have these mistrust scores, we found that they are primarily depending on things like agitation and whether the patient is in pain as extracted from the notes. And when you look at the interaction with race, the median black patient has a statistically significantly higher mistrust score than white patients, but this is not just race. So we look at whether we can explain the treatment disparities by race. You can explain away more of the treatment disparity, more of the gap between populations, using a mistrust score than just using race. So there's an interaction there that's not completely captured by race. And second, a rebuttal that you might have is, well, maybe they're just sicker. And so they're not just sicker, right? Because these acuity scores that are standard in the hospital, like OASIS and SAPS, are correlated with one another, but they are not correlated with a mistrust score. The mistrust score is actually correlated with things like autopsy that we know are related to trust. So that's it for sort of research. There are 3 things that I wanted to cover for future work, or things I think are important before leaving, which are, number 1, ethics is not new in health. Right? So in healthcare, we've had to deal with drug pricing, opioid epidemics, retracted studies, conflicts of interest, clinical trial populations being non-representative. The sort of new thing from my perspective in this community is ethical machine learning, how we do algorithm development correctly. And it's because when you do ML and health, there are questions beyond the obvious, like these human interactions and whether you're making things better or worse by using a model, right? That's learning on biased data. But we already are regulating these things, right? So it's happening. It's not like we can just pretend that it's not a thing. It's actually happening. And so I think it's important to recognize that there is opportunity, because in Eric Topol's paper and new book, he actually highlights that there is at or above human level performance in specific tasks, and so the opportunity is there. So the second thing I want to emphasize is understanding trust in the way that we try to address using these clinical notes in the second study has a real impact. And so we know there have been really, really fascinating studies done on randomizing whether a patient gets preventative treatment advice from somebody of the same race. And it works significantly better in things like likelihood of in-hospital mortality and in getting patients to actually do preventative invasive tests. And a majority of this reduction is in minority populations. So for example, black patients with black doctors. And gender concordance, actually, this is one of my favorite quotes from a paper ever. So in the third study, gender concordance increases a patient's probability of heart attack survival. But mortality rates decrease when male physicians practice with more female colleagues or have treated more female patients in the past. This is worrying for me. Have you seen a computer science auditorium? Like, the gender balance is not great. So what this means is that this is fixable, right? If performance gets better as you work with more women, for example, in this case, and maybe it would get better in other minority groups, right? or women are not a minority group, unless you're in computer science, then maybe we can fix this. Maybe this is something we can address. Maybe people can be trained to interact with different groups that are not the same as them, so that they engender trust. And that would be really, really transformative, because once I was giving a talk in a room of tech CEOs, and one of them raised their hand and asked me, so you're trying to make, algorithms, like cutting edge so that all doctors can be like Dr. House. And I thought, are we watching the same show? Like, do we want doctors to be like Dr. House? He's a drug addict. He's mean to people. So we probably have this wonderful space where we can actually help doctors do better doctoring. Because there's also really fantastic research that demonstrates that the compassionate interaction, and not even a lot of it, just a little of it, improves patient outcomes across a really wide range of conditions. And the final thing I'll say is that we should be treating health data as a resource. There is a play right now amongst companies to lock up data resources in the health space and then operationalize that into products. But we should be creating cutting-edge research with these resources, and we should keep them in the public sphere. Because we as a community have a decision to make. So in the machine learning community, you're on a hiring committee. Every machine learning department, every computer science department hires sort of a theory person in machine learning, and they'll hire a crypto person, they'll hire a vision person. Nobody hires speech people anymore. They haven't for like a decade. Do you know why? It's because 10 years ago, Fei Li made the decision at Stanford to open the ImageNet data set. So vision can be done at state-of-the-art level academically in the open public space. But about 8 years ago, Amazon started their Alexa project, and that data is owned by Amazon. The Google Home data, that's owned by Google. You cannot do cutting-edge speech research in academia. It's not possible. When I have a student come and talk to me, I say, well, unless we have a company giving us that data, there isn't public resource available for you to get the same performance. And so as a machine learning for health community, and I would say as a broader health interested community, we should make a very strong conscious choice, as was made for these communities, about whether we want our data to stay in these spaces. Thank you.
No, we'll use that, and then I'll just speak it now. I'm good.
Okay. Our next speaker is Joan Fujimura from the University of Wisconsin. I'll just comment. In general, we're going in alphabetical order unless the panelists in a given panel have chosen some other order.
I see, okay.
And prepare your questions
Thank you.
for the
Now, where does it show?
session, which will be following the break after the panelists speak.
Okay, well, I don't have solutions, so I'm really happy to be here to talk with everyone. And I really, so I'm going to be presenting the problem rather than solutions, but I hope we can come up with something. Okay, so where am I? So I've put everything on the slide, so hopefully we can, I have too many slides, so I will try to go quickly. So I don't know if I need to say this to this crowd, but in contrast to 19th century European anthropologists and biologists who classified humans into what they considered to be biologically different racial categories, everybody else, it seems, historians, sociologists, anthropologists, some biologists, hopefully computer scientists, have been writing about races as not being equivalent to genetic or biologically distinct populations. Especially since World War II, social science and historical researchers have emphasized that race and ethnic categories are social, political, and historical constructions that differ by locale and era. But in the 21st century, conceptions of racial groups as almost equivalent, different genetic groups has been on the rise again, especially with respect to certain members of media. We all love to hate certain, I won't go into that. I took that slide out. But also by social scientists and sociologists, and some in my department have been talking about races as genetic categories. So this is where my concern comes from, and the concern of my group. So the larger context then is the resurgence of racial genetics was the transformation of biology into big biology, big data. So that's what I'll be talking about today. Medical geneticists built data infrastructures to allow them to conduct large-scale analyses to search for genomic risks for disease, common complex disease, among the 3 billion DNA-based bears. So we studied the processes by which geneticists built big data infrastructures and how the information produced by those data infrastructures was used in medical genomics research. We're ethnographers, so we go and live in the lab and interview people and study their algorithms and study their databases. Okay, so genomic risk markers for common complex disease, and compared to clearly population-linked diseases caused by single genes, so we all know what those are, but I can talk about it. Common complex disease research focuses, of the 2000s, focused on efforts to locate genomic risk markers for CCDs. Researchers were hoping that they could find genomic markers or SNPs, and I'll talk about that more, that would lead them to genes for disease. Now the scene has changed entirely because it's been very difficult to identify genes for disease. So now the SNPs have become risk markers themselves. So they've been transformed into risk markers. But people forget about that early history. The constructed genome-wide association study, there should be a Y, which are large-scale studies that use statistical methods to search for associations between single nucleotide polymorphisms or SNP differences between people with the disease and without the disease. So there's cases and controls. Okay, am I saying what people already know?
No.
Okay, good.
Just maybe you can have an extra couple minutes. Just slow down a little because it's a lot of information and it's fascinating.
Okay. Well, I have 30 slides, but I will stop when I stop. I have cut from 45, but I will stop. I have major conclusions at the end, but I will stop. I think it's important to get this information out, so I will stop when I have to stop. So just let me know when I have to stop. Okay. So SNPs. So at the beginning, they estimated that they were 0.1% of the genome or 0.5. Now the number moves around, but so you know that we have 3 billion nucleotides, and so this means that there are about 5 million nucleotides differences. That's very few, really, when you think about it. Okay, I have a slide that shows that right. So, beginning with the Human Genome Project, genetics moved. Okay, sorry, I changed. Moved to big data genetics, and in this case, statistical genomic epidemiology. They built infrastructures as shortcuts to find markers that would lead them to the many genes they suspected were involved in common complex diseases. But each infrastructure was not enough, so they built another. And we have a history of the infrastructures in the book, which is not out yet, but we'll get it out. at this time, we have layers of infrastructures, each supporting the other and each based on the other, but in complicated ways. So now we're in the time of big science and big data. So these are just some of the infrastructures. So they started with the Human Genome Project, but of course, there were several projects before that. The haplotype mapping project, but there were several projects before that. Genome-wide association studies is what we've been talking about. Technologies like Eigenstrut is basically a PCA, principal component analysis, standard in statistics, but Eigenstrut was a particular version of it. Since then, there are multiple versions of it. It's sweeping the world. That's the scary part, because that's the part that makes populations. And so we're looking at genomic differences and genomic clusters. These clusters were produced by the Eigenstrut program, actually by the sub-programs within the Eigenstrut program. And they've been read by people in the media, genetics, and even sociologists as showing that racial categories map onto genetically different categories, which is not true, but it looks like it to them. Okay, so I just wanted to give a sense that there were different attempts before the HAPMAP project became the final choice of the National Institutes of Health. So the DNA polymorphism discovery resource was one, the SNP consortium in 2001, and then we ended up with the haplotype mapping project. So the winner, of course, is a population-based sampling strategy that includes the identification of a population, and I'll say more about that, using the advice of human population geneticists. The medical geneticists collected DNA from specific groups of people in different countries. They identified the groups in that first version of the HAPMAP as the Yoruba and Ibadan, Nigeria, the Japanese in Tokyo, Han Chinese in Beijing, who became part of the project when they found out that the Japanese were part of the project. But of course, the geneticists thought, oh, well, the Chinese and the Japanese are the same, so we only need one. So different views. Utah residents with Northern and Western European ancestry, most of them were from the Mormon communities. So it's a very interesting data set. They were not labeled as Caucasian, African, Japanese, Chinese, or Asian even. But if you sit in the lab, of course, everybody uses these terms. But then when they look at me sitting in the lab at the table, they switch to these formal names. And they're always supposed to use these formal names. But okay, the HAPMAP project design included practices that shaped the subsequent use of the HAPMAP data. So, in other words, the ways in which the groups were labeled, even in HAPMAP 3, shaped their subsequent use in GWAS studies. So, there are social identifiers by race, ethnicity, nation, city. Or, for example, in HAPMAP 3, they said the Gujarati in Texas. So, they were still identified as the Gujarati, but they were in Texas this time. So, this is the conceptual place in which notions of groups and other group identifiers entered the search for genomic disease risk markers. Let's see. So now, so how did race become genomic? Again, this is not what I believe. So I just wanted to put the two major points that I try to talk about in detail, but I won't have enough time. But the International Haplotype Mapping Project produced these data sets, okay? DNA data sets that were used. The Eigenstrut or PCA technology was used to analyze it and produced plots that basically represented populations. So, and as I said, more similar technologies have been developed. Okay, so the Eigenstrut compares DNA across samples and generates genetic variation scores. And they use these scores to look for genetic associations for disease. We can talk about that in more detail, but you don't need that right now. The HAPMAP selects particular SNPs by population. The SNPs were chosen from groups identified by racial, ethnic, national, city names. These SNPs were then became reference SNPs to be used in statistical epidemiological studies, genetic epidemiological studies. So to authenticate the SNPs of the individuals and groups used in study populations. So we're talking about the HAPMAP samples used as reference populations to authenticate the SNPs that were used in study populations. So, okay. Okay. So I'm going to just give you some big conclusions now, and we can talk more later. As geneticists began to build big data structures, their sociocultural assumptions about race entered into their scientific research practices and became entrenched in their data infrastructures. These data infrastructures formed the basis of subsequent research, some of which made it appear as if races were genetic categories. So infrastructures were built step by step to search for genes for CCD, but because of these cultural assumptions, because cultural assumptions about race were built into several infrastructures, using these infrastructures, human geneticists constructed group population genetic differences, which looked like races were equivalent. So I just want to be clear that, I'm not saying that all population geneticists should disappear from the face of the earth, although some people have said that. But I want to make clear that they are doing a particular kind of work, and their work produces populations, which are technical categories for them, for whatever they want to do with it, their purposes. They understand that they're working with these tools under particular conditions. They have limited time, money, technologies, and the technologies change through time, so we're still studying it. They take shortcuts, they make accommodations for their limitations. They also work with certain political demands. So all of these produce first approximations, and genomic clusters are one outcome of their exploratory technologies. So they refer to their genetic clusters as populations. And populations are not races, I want to make that clear. Population geneticists construct populations as a set of genetic categories using particular tools for particular purposes. Let's see, in this case, searching for SNPs. They're not meant to represent real people in real groups in the world. And I have to say this over and over, actually. Racialized groups are historical productions made up of people with histories in societies, in particular societies. Races aren't populations. Races are social designations that differ by context, including nation, different areas within a nation, different historical periods, institutional purposes, histories, individual identity, self-designations. I mean, just think about the way how people self-identify in this country alone, across the U.S. It's different. I mean, I've been living in Hawaii for the past year on staff. And it's, we can talk about the different self-identifiers that are going on now. Okay, racialized groups, Omi and Winan, 1986, I stand by that. This is Dick Lewontin's 1972 statement based, admittedly, on a different set of data, but it still stands. Genetic differences within a racial group are greater than the genetic differences between racial groups. But infrastructures are not innocent. They carry with them practices, some of which become embedded in the infrastructure. The HAPMAP is only one such infrastructure that incorporated notions of population differences that could be read as ancestral differences, that could be read by some downstream users as racial differences. Cultural assumptions were built in throughout, and that's one of the things that we're showing in the larger book, where cultural assumptions get built in every step of the infrastructure. So we say that we're basically doing an archaeology of infrastructures. Infrastructures were built from the bottom up. Let's see. Any populations constructed through these choices and infrastructures are scientific work objects and not groups of real people in the world. So the takeaway is that the populations constructed by population geneticists don't say anything meaningful about the biology of the groups. The ability to construct a cluster or a population is not meaningful in the context of traits, especially for the health purposes here. Data is already structured. I'm saying always already structured. In high school, your teacher tells you never to use the word always when you write, but I will say that here. Raw data is an oxymoron. But the last slide that I just wrote is, yes, so I already gave it to you. GWAS may soon disappear. There's been a lot of critique of GWAS studies. But population clusters from various algorithmic programs are proliferating and spreading across the world. And every group thinks that they have produced the best algorithm for constructing population differences based on this data that has been built into the infrastructures, based on the data collected through the HAPMAP and the comparisons, the particular SNPs selected by the HAPMAP and the comparisons with the study populations. So we can talk more about this. Pilar Osorio is a bioethicist who has been part of this project off and on. Ramya Rajagopalan is a geneticist who joined our group, and Shel Doksum is our statistician. He taught here for many years in statistics. Lucky man is retired. Okay, thank you.
Third speaker is Nancy Krieger from Harvard.
Oh, wait, I have this. I walked away with your mic.
Everything.
So I'm very glad to be here today, and I really appreciate the invitation. I'm hoping very much to learn from people who are in very different disciplines than mine. I'm a social epidemiologist. I'm someone who's steeped in the history of public health, epidemiologic theories of disease distribution, and the politics of public health data. Usually I tend to give very formal talks, but in the spirit of this being a workshop, I have some key points and essentially want to riff off of them. And I'm going to start with a way of first being transparent, which is that my vantage point is that of the ecosocial theory of disease distribution, which I first articulated in 1994 and have been elaborating since. We live embodied. This means that when we look at our health and we look at our being, we look at ourselves and our bodies at any point in time, we are always embodying the world in which we live, both the social world and the biophysical world, the larger ecologic context. And there is no way of understanding our health without bringing both of those into play and seeing how it comes into our bodies, which is then what we re-experience and can call our health status and or disease status. And that this is essential to understand population patterns of health, disease, and well-being, especially how they change over time, and also the magnitude of health inequities defined in multiple dimensions, whether in relation to race, ethnicity, economics, other aspects of class, immigration, refugee status, nativity, as well as gender, sexuality, etc. The other thing is that when we always think about embodiment, we have to think about pathways embodiment, and this includes understanding how injustice structures the worlds in which we live, and also how equity can structure the worlds in which we live, and what that means for human health. This means looking at the cumulative interplay of exposure, susceptibility, and resistance at multiple levels across the life course and historical generation. So when you think about studying any population, it's at a real time, in a real place, in a real society. It's not just something called a population that's floating around in the cloud or elsewhere. And that there's always multiple levels from macro to micro, and they're all within us. And so it's really key that we understand there are huge distinctions between what I would call biological expressions of injustice, that is how we get health inequities that reflect through the body, and and that includes, in my mind, that mind is in the body, so it's both somatic and mental health, or And that can be due, again, to the many forms of injustice that we have, versus what are unjust interpretations of biology, which are premised on notions of the long histories of scientific racism, scientific sexism, the list goes on and on and on, where interpretations of biology are completely biased by the injustice that affects how people think, and that is nothing new. And it's also really important, building on points that you were making, to always understand what the metaphors and mechanisms are that are being invoked to explain patterns of disease distribution at any point in time and how they are contested. And another point is that there is always a contest between ideas. There are almost always dominant versus alternative framings. We live in a point in time where the dominant is biomedical individualism, bringing in a social justice and a social determinants of health standpoint, or if you're in Latin America, it might be called collective health, or it might be called social medicine. It would give you a very different vantage point. So to assume that there is just one way of knowing and interpreting what the epidemiologic data are and the theories that are used is not true. There's actually lively context. Other points, building partly off of what Joan was saying, is that data never speak for themselves. The word data comes from Latin. It's the past participle of dare, which means that which is, what dare means to give. Datum is that which is given. Nothing's ever given. People always obtain data, they analyze data, and they interpret data. So, and that's always, again, in the context of their times, and whether that is challenging dominant frameworks, for example, in the United States, challenging dominant frameworks of white supremacy, versus actually in just going along with them, which is what a lot of the science does. So nothing is ever given. We work, and we work hard to do our science. And what it also means is that we need to have historically informed theories, not just data, to evaluate the quality and biases of data, including, as per the first speaker in part, who and what is missing. And that's, again, very much in terms of the context of the long history of scientific racism in its many guises, which in this country was uniquely formed in the context of the history of settler colonialism and enslavement, and the expropriation of the wealth and denial of rights, community, cultures, and humanity of indigenous and enslaved populations. And this history has informed each and every generation's debates over patterns of population health and health inequities, very much so about the impact of racism on health versus is it because people are just somehow uniquely different and there are racial superiority and inferiority. Give me a technology in health, there will have been a debate about this around racial inequality in health. It just keeps coming up. We're at the time we are in our history with the new technologies, both in the computing sciences and the biological sciences, to have new sets of debates. And I'll be giving concrete examples. So another corollary is that we need to have historically informed theories, not just data, to understand the kinds of structural injustice that exist and that shape not only conscious and unconscious bias, but even the incentives for building systems of data, including artificial intelligence, and to what end. And that means also, and ties very much to your first comments about understanding what are the incentives that come with individualism and methodological individualism, and assuming that you can just get data off of people and somehow get that from that to quote unquote populations, versus understanding that you need to start actually with structural data. And where does that take you in understanding how individuals are embedded within structures and societies and contexts? So the last sort of general theoretical point before coming to some concrete examples is that you also need an awareness of history as a precondition to predicting the future. Because otherwise what will happen is if you do a naive prediction off of what we have now, it means injustice will continue in perpetuity. How do you understand change? And how do you understand the human capacity to imagine and to create, not just simply destroy and consume? To predict a future based on past injustice is a political, not an empirical choice. So I can even just name the changes that have happened in my lifetime, given my age. I mean, I was born in the US and in 1958, so that means that I was alive when it was the 1964 Civil Rights Act, the 1965 Voting Rights Act, the 1968 Fair Housing Act, all part of the abolition of legal Jim Crow, as well as the creation of the Environmental Protection Agency, the Occupational Safety and Health Administration, new levels of regulations of environmental occupational exposures, legalization of abortion, Roe versus Wade, of course, legalization also more recently of same-sex marriage. And these are all things now subject to severe backlash. This all affects health. How can we understand the health that's seen in records without contextualizing the historical context and what that means for the changes of the diminution and then the expansion of health inequities? So let me now give some empirical examples and where there are key problems and pitfalls. Looking at uncritical applications of AI to population health data has the potential to cause harm and it already has caused harm. And to organize my examples, I rely on a schema that I've recently developed for a paper that's under review right now to talk about structural measures, individual level measures, and individual of exposure, and also internalized measures of exposure to racism. And with the structural, it's really important to be clear that there are first, what are the unjust rules of the game? Those are rules that explicitly discriminate on the basis of race ethnicity, as happened, for example, with Jim Crow and also with historical redlining, which is about the government-supported legal residential segregation in the 1930s that has had its impact on neighborhood trajectories. Remember, neighborhoods have trajectories, not just people. There are the implicit unjust rules. So for example, when you do things sleight of hand, you have a poll tax. This doesn't mention race per se, but it's clearly meant with racial animus and racial bias. This really matters in terms of jurisprudence, in terms of whether you're supposed to prove intent versus whether you look at inequities and outcomes. And then there's a lot that's in the literature right now that's being called structural. That's really area-based measures of group differences and lumping them in indices. So if you look at differences in employment and education levels and income, whatnot, you come up with an index and you call it structural. And I'm not quite sure that really is structural, but it is an area-based that reflects the footprint of what have been other kinds of practices and systemic practices that lead to what those group differences are. The individual level at the exposure is about people self-reporting their experiences of racial discrimination. And those are always things that you have to always have caveats about, because there's a lot of things that affect what people will say in terms of whether they are able to articulate what their experiences are, whether they trust you, the forum, whatever, to report those experiences. And there's ways to deal with what those kinds of biases are. But a lot of studies don't do that. And you can never take these data at face value. And then similarly, you'll have measures, as I said, of the internalized racism, which are all three levels, which can affect how people interact with others, treat themselves and their own bodies. What does that mean in terms of what their health status will be? So to give some examples empirically, first, if one relies only on individual level medical records and medical data as collected in most hospital settings, separate from the question of how badly the racial ethnic data are collected, because there's still a lot of data that just comes from the medical record that was decided by the medical staff and never actually asked the patient, and very bad systemization of what those data are across records, it means you will have absolutely zippo data on whether people self-report any experiences of racism, what their internal racism is, but above all, you'll have absolutely no structural measures. And you rarely will have measures that even contextualize what kind of, were they seen in a community health center versus what the funding is. You have states in the US which have terrible Medicaid policies, and you have states which have better Medicaid policies. Massachusetts, where I'm from, is somewhat better. But if you don't know what's going on in the system level, all you're going to see is what's reflected in an individual patient's record, which gets back to the individual level individualism and methodologically that says that you can just study lots of individuals and that equals understanding of populations. It doesn't. There's the long reach of history. For example, not only is that you don't know the current context, but I'm doing work, for example, that shows the continued impact of Jim Crow on the health of people who are living now. Been looking at that specifically in relation to Jim Crow and breast cancer estrogen receptor status, which is really important in terms of therapeutics and what it means for the likelihood, and showing that there's a strong Jim Crow effect for African American women and not white women, that if they're born in a Jim Crow state, it matters for the kinds of breast cancer estrogen receptor status that they have going forward now. And that's not ancient history, because when you think about embodied history, you know, it's like a lot of people that are sick and getting chronic medical care now and dying are in their 60s, 70s, 80s. Hello, when was Jim Crow legal? When were they born? When were their parents born? What does that mean? That kind of understanding of history gets completely lost in frames that look just at the patient data now and just at the individual level. Similarly, you can look and well, I want to go through a bunch of examples. I'm mindful of time. So the other thing is that it's also really important to be aware that people are using in some of the epidemiologic studies, quote unquote, big data coming from the internet. I saw there's something in the title of this conference about not internet data, but are being used as structural measures of racism. But the thing is, again, you have to ask in what context, because if you also look like the latest NAACP report on the use of the deliberate escalation of anti-black rhetoric online for the 2016 elections, and what that means, that there's a lot that is fomented as well as comes from what is ever else going on in the US. How do you treat, you can't treat those data at face value either if you don't understand something about context. And so I think these are all, and then the last thing to say about the contextual and structural level is in Topol's new book on big data and medicine. There's this astounding chart at the end, which has this thing that looks at the different levels that you could look at data. So there's like, from the person on down, there are a zillion levels about every single omics that you can imagine. And then there's one line at the top about social context. That's the problem in a really big way. And so I think that it's really key to understand that actually I could extend, and people that are even in the social sciences could take that one and go like A, way up, and B, understand that you're looking at an individual at a moment in time. What is that time historically, as well as where they are actually in their individual life course in terms of infant, young toddler, kid, adult, et cetera. Secondly, this has been alluded to by other speakers, there's huge issues if you're going to be dealing with quote unquote medical or public health data about classification, misclassification, and exclusion is tied to the histories of scientific racism and the politics of public health data. For example, consider the data on what the group that gets lumped by US Census terms as American Indian, Alaska Native in the United States. There has been a lot of work to try to fix the incorrect misclassification in mortality records. And actually, over time, the amount of misclassification of race ethnicity in terms of you ask people and you compare it to what they said before, what they say, no, obviously they don't say anything when they're dead, but before they died, or else what family members say, you'll see that it's virtually non-existent misclassification now for people that are labeled quote unquote white and black, almost non-existent, about 3% for Hispanic. It's 40% for American Indian, Alaska Native. And that means, and it also, of course, varies by region of country depending on which nations and tribes are involved. And what that also means is that there actually are some very good work that's underway right now that's being led by some of the American Indian epidemiologic units that are attached to both IHS and also freestanding, because urban Indians are, of course, not covered by the IHS, is to actually try to start combining data across health records and also with data linkage and concerns about privacy, Social Security, employment records, whatnot, to try to come up with better data. Because if you've got terrible numerator data and terrible denominator data, guess what? You get terrible rates. It's just a given. So that's a place where you could see that there could be really helpful use of AI to help work on that. But if you don't understand what the problem is socially, politically, and historically, and also to understand the different histories of the miscegenation laws that have happened in this country around American Indians and not just African Americans, you don't understand what that story is. Similarly, it's also really clear that you measuring, and this has been alluded to, measuring something like race, even self-reported, is not the same as asking whether you've smoked cigarettes or not. It's a very different kind of category. It's not the stable little variable. Looking at the data on the exit of who changes, what's called by some of the demographers racial churning, who reports what race in 2010 versus 2000 census, you get a lot of churning. What a kid says when the parent's in the room versus when the parent's not in the room, you get changes. That's part of understanding the social lived reality of what this race ethnicity. So it looks like a nice, neat little variable in your data set. It never is that. And it also matters, by the way, on the nativity and immigration, is that there's increasing work that's now showing that you can't just talk about immigration, healthy immigrant effects, because it also depends if people are refugees. And as we're watching what's happening now with the immigrants coming across the border that was referred to by the first speaker, if you've got some of the conditions of health and the people that are dying now in detention centers, I wouldn't call that a healthy immigrant effect. Similarly, how people are deciding to also cluster data and talk about data, or talk about groups of outcomes. If you don't understand the history of scientific racism, you don't get it. So there's this whole discourse now about deaths of despair. That's about basically looking at mortality due to opioids predominantly among white populations of particularly middle age. There's also really interesting work that, if you want to call it deaths of despair, to look at homicide rates. Not just suicide rates, but also homicide rates that are happening in, for example, specifically the contrast often made to African American communities. Aren't those deaths of despair? So not understanding what the lens is means framings of problems that can be really problematic, and they're not just intuitive from the data. The last point for many of you who might be playing with population-based data, population survey data, all the huge big US surveys are done on the non-institutionalized civilian population. Well, that's a lot of people, fine, except A, who's missing? Everyone who's incarcerated. B, everyone in the military, and C, everyone who is otherwise institutionalized. That really matters if you're concerned about inequities. and you miss them. And there's been really interesting work that's been done more in sociology, looking at, for example, if you try to look at the black-white differences in income or employment, if you lop off the incarcerated population, you end up with really distorted understandings of what the progress is or not. There's been a little work like that in health, but not enough. So it's, again, if you're really trying to think about how do you understand who's missing and who isn't systematically and why, in the data that's going to be analyzed, this is more than just about external validity. This is also about entire ranges of exposures that are not adequately being considered. So the last points that I want to bring up are ones that are about the unjust rules of the game that can happen in algorithms. And they were already alluded to by the first speaker about diagnostic biases. There's been really clear work that shows differential approaches to appraising pain, and also differential accuracy in diagnosis. But there's also the question of whether certain therapies or interventions bring in a, quote, race lens or not. And so there's a paper that's just come out about challenging what is done uniquely in the US of a, quote unquote, race correction for vaginal birth after cesarean section, when no such race data are included, for example, in Canadian data and in European data, and instead looking at mainly the economic indicators as well as age, and also that funny thing called comorbidity, because people remember, we're all in one body. So you don't just sort of have an illness. You usually have an illness in the context of a lot of other things going on. People don't just, per that prior example, people routinely have diabetes, hypertension, and sometimes cancer at the same time. And it seems to be, I do a lot of work in the cancer world, and it's like always a huge discovery to people that there's multimorbidity. It's like, really? And how does that mean? If you don't take those parts together, you've got a real problem in understanding who is being studied how with what inclusion criteria, and that really matters. And I say this on a premise of saying that as humans, by and large, we have pretty similar biology, and it's not a good deal to have diabetes, cancer, and hypertension at the same time. And what that's going to mean for treatment, and what it's going to mean for treatment, not only in the medical terms, but also what it means for somebody in the context of their family and support, if they even have a family. It's really important to take that into account. So the last point is that it's really important also in the little bit that I've been looking at some of the kinds of claims that are going to be made on better predicting things. There's a lot of framing of delay in seeking care in the cancer literature. Particularly, you can see this in cervical cancer. What this completely misses is that it puts it back on, just like with quote-unquote non-compliance, it puts it completely on the patient. It's not like, what's the transportation system? How are they followed? Is there a patient navigator or not? Who makes sure that things happen? Because a lot of women get the screens for cervical cancer, but then they never get treated. They fall in between the huge crack. And then it's called delay in seeking care. But it puts it on the person. If we don't have systemic analyses that take into account the structural factors of what the incentives are about who gets treated, how, who's brought in, who's moved along, we end up with these inequities that always end up getting put back to the bias of individual methodologic approaches and just strong individualism. It gets put back on the person, like they delayed seeking their care, not what were all the obstacles to their care. And you will not find those obstacles in people's medical records by themselves. You always have to link to other data sets. I've helped people at one of the hospitals in Boston show where the diabetes patients that are having the most trouble, they're in the transportation, quote unquote, deserts in Boston. And if you think that you can park your car near any of the major Boston hospitals, good luck, especially if you don't want to lose over a day's worth of wages for the parking lot. And the last point there too is that in terms of the appraisal of qualities of care, again, very few indicators in any way will show up quality of care in relation to people's experiences of racism. And I think that, I actually differ a little bit on the framing of trust. A lot of the trust literature in the in the epidemiologic research has not really engaged well with why there is. The mistrust is seen that the patient has a problem to fix, as opposed to there's a problem in the systemic racism in the health institutions. So my only points then is that to work with big data and to work with computer algorithms and to work with health data is to really understand that we need to grapple with history, understand the moment in which you're doing the research, understand what the theories are that you need to bring that give the array of exposures that are at multiple levels happening over time in life course as well as historical generation, to understand the errors of omission and commission in the population health data that will be fed into the algorithms, and that these errors will be compounded and not reduced if one relies only on the existing individual level health data and do not take into account both the biases of this level and the failure to include the relevant contextual data on exposure to racism at multiple levels and historical context. So that's my risk.
And Dorothy? Oh, no, sorry, Sendhil. Mine is just. Okay, so next speaker is Sendhil Mullainathan from the University of Chicago. I seem to walk away.
All right. Okay, thank you for having me. I'm going to talk about two papers today. It's with quite a array of people that I've listed here, but they're primarily the work of Emma Pearson, one of them, and then Ziad Obermeyer for the other. At this stage in my career, I'm not really sure what my role is. So basically what I'd like to do is talk about two empirical projects that try to touch, that are really just sort of in healthcare, and I thought both of them touched on the role of algorithms and inequity in the delivery of healthcare. I think they each tells a very different story, quite distinct, I think, but yet I think each story is itself typical of a kind of thing that we've encountered in our work. By background, I used to do a lot of work, empirical work in behavioral science, having focused on discrimination. In the last 5 years, I've been working a lot on machine learning applications. And so for me, this area is one where I come at it with the sort of the dual lens of thinking about human bias and also just thinking about the potential for algorithm bias. And so both of these narratives, both of these papers speak to that. So the first one involves something Nancy touched on, which is comorbidity. For those of you who don't know, care coordination programs are a pretty common program in the United States and increasingly around the world. And the basic point of care coordination program is to recognize that if you look at healthcare costs, a fraction of people account for a lot of costs. And in particular, it's people with these many comorbidities. They are people who've got a lot going on. And these people are in many ways the epicenter of costs. And programs have been designed to target these people with extra resources. So it kind of makes sense that if you're going to show up a lot at the hospital or at your ER or whatever it might be, that we ought to treat you differently. So these programs are actually very good, and if you could, you'd love to be enrolled in them. For example, typically you get a nurse assigned to you. And so whenever you feel anything, you're asked to call the nurse. And then the nurse will tell you whether to come in or not. And then when you went in, you have your own special lane. You don't go to the front desk. They know you're coming, and you go straight and you're taken care of immediately. One of the things that people hate in this literature is to refer to these programs as frequent flyer programs. But so I won't do that. I'm learning from our president on how to talk. To target patients, we have to decide who is eligible for a care coordination program. These are expensive, so we want to give them. And it turns out, we often talk in this literature on algorithms that could be scaled. This is one of the largest kind of algorithm that is already used at scale. There's probably about over 100 million patients every year run through these algorithms to decide who is going to get a care coordination program. So what I want to do today in this first project is to ask, let's take one of these live algorithms. We have one from one company, and it's kind of the largest, one of the largest companies in this space, probably a little more than, it's hard to get exact numbers. Let's say tens of millions of people are run through this program, through this algorithm. And so it exists. And what I want to look at is, well, how inequitable is this program? Is this algorithm? And I want to in particular look at equity through the lens of who's getting into the program. So we're trying to get the sickest people. And so let's ask the question, what kinds of, and we're just going to use whites and blacks for now, what kinds of whites and blacks are let into the program. And specifically, I'm just going to look at a simple calibration curve. Given a score that the algorithm has outputted, at every score level, what is the realized health of whites or blacks? Very straightforward. There are other things we can use, and we can get into that discussion, and there's amazing literature on these things, but this is just as an empirical exercise a good place to start. Now, we've got a bunch of measures, but in the interest of time, I'm going to show you something called the Gagne score, which is a pretty good summary statistic of your, I'm not even sure I'm saying that right, but it sounds more fancy. It's Gagne. I'm sure there are plenty of ways to pronounce that, but I'm pretty sure Gagne can't say my last name either, so so what I want to do is I want to put the score up for that, and if people are interested, we've done this for many measures that might be more familiar to you, such as HbA1c, which is a measure for diabetes or blood pressure or things like that. But here's what we have. We have the risk score on the x-axis, and then by race, we've got the realized health. And what you can see is that at every level of the score, blacks are sicker, and quite a bit sicker. So for example, the auto-enrollment threshold for this program is right here. This is the 97 point. If you're at this score, you auto-enrolled in this program. The gap, if we zoom in, have 28% more chronic illnesses for blacks at this threshold than the equivalent white at the same score level. And it's true of many other health outcomes, as I just said. Let's go through a calculation of how big this effect is through a very simple simulation, like super trivial. The super simulation is, let's zoom into this area. I just did this because my co-author made this, and I just think it's amazing to zoom in. So what you have is zoomed into that region. This is the curve for blacks, the curve for whites. What would it mean to equalize? It would mean, wow, these very sick blacks are not getting in, and these far less sick whites are getting in. Let's simulate adding and replacing until we have an equal. So we're going to add those people into the program, remove those people until we reach sort of a same health score. If we did that, the fraction of blacks in the program would double from about 17.7% to 36.1%. So the gap is very sizable. So what's happening? Where's the algorithm going wrong? And I should say, by the end of this, I hope you'll see, this one manufacturer, I think, is got this problem, but I'm almost certain they all have this problem once you see what I think is happening. So where's the algorithm going wrong? So there's a lot we can get into. We could talk about the underlying data. We could talk about how there are biases in the data they're training on, and surely they all could be playing a role. But one telltale sign of where the algorithm is going wrong is actually where the algorithm is going right. So I put health on the y-axis. Now, a different thing I could have put on the y-axis, a similar calibration curve, is not looking at calibration by health, but looking at calibration by dollars spent. And it turns out perfectly calibrated, no racial gap whatsoever. It's kind of interesting. And so what's happening? So the problem is that I gave you this narrative about we're trying to get the sicker people, et cetera. But healthcare costs are not the same as health outcomes. In the policy literature, people are both careful about this distinction and also kind of free and loose about this distinction. Because empirically, costs are health. I mean, if you get a claims database, actually, you're not looking at health. You're actually kind of looking just at dollars. What is insurance claims? And why does this matter? It's because if I put health on the x, and just in the interest of time, I won't go through this. It's obvious to all of you. But if you put health on the x-axis and put costs on the y-axis, guess what? Those two are positively related, very strongly positively related. But on the other hand, there's a gap. At the same level of health, blacks end up costing less. So the previous speaker mentioned access issues about people showing up, et cetera. So there's a big difference. And it's simply whites have better access to health care. And at every level of health, blacks cost less. So accurate cost prediction, unbiased accurate cost prediction, which is what we have here, does not mean that we have unbiased health prediction. We actually have pretty biased health prediction. So as I dissect the problem, there's a proximate cause, the label. The algorithm is optimizing one objective, the objective it was given. In this case, they were building costs. But that's not our full objective. We have, we care about health as a society. But I think that misses the point a little bit, which is we now should dig a little deeper. And for this, I cannot give you firm answers, but I can give you some speculation before moving on. Why was cost chosen and not health? Because after all, somebody chose that label. And not just one person. There was a whole system choosing this label. The algorithm manufacturer, the purchaser of these algorithms. So, what are two things? Well, as an economist, or maybe I don't have my passport anymore. I'm not sure. But maybe all the guards are at the real border, and I'm still allowed in. I'm not sure. But as a former economist, you might say, this is obvious. It's incentives. Follow the money. Hospitals and insurers care about dollars. Society cares about health. Why do you expect insurers and hospitals to focus on health? Or less extremely, health systems care more about costs than we do. And you could say, look, you're not rediscovering, you're rediscovering an old, obvious thing we've known about healthcare, independent of algorithms, just in the structure of these systems. Many problems in healthcare and healthcare delivery arise from the incentive problem that the deliverer is worried about costs, and we as a society care about health net of costs. Externalities abound in healthcare. This is simply an example of an externality. So I think the follow the money incentive externality view at least has some, our priors should be there. Let me propose a second view. It's misunderstanding. And I could put this view in a few ways. It's first worth noting, even in policy conversations, we conveniently use costs to talk about health. It's easy to find papers published in good journals, important papers, where they talk in the abstract about health. You dig deep and you're like, oh, they're actually using costs. It's just, they're interchangeable in a way. And the cost label was chosen through a combination of convenience and simply not understanding the consequences. Because in most papers you work on, using cost versus health, because they're so highly correlated, the error is like, well, okay, I could get much better health data, but the cost data is much easier to get, and the error is some approximable error. Now, one reason I'm more prone to the misunderstanding view, the first speaker I thought highlighted it beautifully. Whoa, it's early days and things. We just don't understand stuff. And so these algorithms are going to scale, but it's not clear we understand all of the dangers imposed in them. So it's totally possible there is just misunderstanding. And the differences matters. If you believe it's the incentive view, we need pretty large policy correctives like we need elsewhere in the health system, and that's reasonable. And if you believe in the latter view, the misunderstanding view, then I think we need a lot more work by like people in this audience and to get things out there, because it is the work we do that is going to have dramatic effect. I don't have an answer, but I will give you one little clue. After we did all this, I don't know why we did this. Actually, you might ask, why didn't you do this earlier? But after the paper was finished, we said, well, why not simply contact the algorithm manufacturer? Hey, you've got this algorithm. Isn't this a problem? I don't know what your prior is. I can tell you what my prior was.
Who's the manufacturer?
Oh, I'm not going to, I can say if you'd like, but I think I'm going to not say at this point. And here's why I don't want to say. It's just a choice. I think by implying them, I think as you see the problem I described, all of the algorithms in this space do this. And I would rather not say, oh, they did. It's not. The entire space is complicit in this. And it is, you just pick one. They all did this. So I don't know about your prior, but my prior I can, by reveal preference, my prior was revealed by the fact that I said to Ziad, why don't you contact them? And so, turns out they were super responsive. They said, my God, can we work with you to try and understand the problem and fix it? They then took our thing, replicated it in their data on sort of 3.7 million patients and said, yeah, well, there does seem to be something. Then they proceeded to ask, well, what kind of fixes could we get? And started trying to build fixes. I don't know what that means. You can be cynical and say they're front-running a problem, a publicity problem before I have no idea. I'm just telling you the facts, and it made me think there's some complexity to this issue that is different than I might have thought. Okay, so I'll skip this in the interest of time. This is the method they're developing the correct. I think we can do better. I think that, but already they've sort of had an 84% reduction of the problem. But I think it's the kind of thing where if as more people work on it, they at least would be open to implementing it. Okay, so let me move to the second project. Okay, so first story, I hope it's kind of clear. The second project comes from something in the world of social insurance. I've worked on poverty in the past, and one of the more striking facts about US social policy that people don't understand is that I think, well, I don't know if many of you know about redistributive programs like EITC. EITC is one of the big redistributive programs. What most people don't understand is that disability insurance has become one of the major transfer programs in the United States. If you simply look at dollars going to the poor over the last 30 years, disability insurance is a big source of it. More importantly, the most common source of disability is arthritis and back, knee, spine problems. So it's actually, if you said, what is a big correlate of poverty and getting resources in the United States, you'd actually end up with osteoarthritis, which you don't really think of. And it's the most common joint disorder in the United States. About 10% of people over 60 and 13% of people, women over 60 have knee arthritis. Here's how we know how arthritis is bad. You take an X-ray, and clinicians look at the X-ray. There's a name for these clinicians, but I can't say that word, so I'm just going to say clinician. And then they grade it. They say, oh, look at this knee. Unlikely to have arthritis, and then it's mild, moderate, severe. So there's a good grading system, established clinical protocols. And the higher the grade, the worse. And so any grade above 2, you're classified as having osteoarthritis. But we have a different way to understand what the patient is feeling, which is we can ask them. So something called the Kuss pain score, which amongst its most frustrating features is that a higher Kuss pain score means less pain. It makes sense, so sure. I just think they wanted you to, every time you use it, feel a little pain yourself, which I thought, it's brilliant in its own way, I will admit. So we can also ask patients, how are you, your pain level? And if you ask them your pain level, you find a striking fact that's been found repeatedly, and David Cutler, who's co-author on this paper, has this fact in another paper, and I just found it striking, which is at every level of severity judged by clinicians, those of lower SES, I'll focus on black-white today, but you find it with college and not college income levels, those of lower SES experience more pain. Same clinical severity, more pain. This has some consequences. Since the severity grade influences whether you get a surgery or you're just told to just live with it or here, take some painkillers, it means that given a level of pain, blacks are more likely to be not given treatment for that pain that's surgically. They said, hey, this is just a lifestyle. You just need to live with this thing. Okay, so I'll skip that. Why is there a pain gap? Part of why I got interested in this literature is that it is a pretty evocative idea that there's this pain gap because it matches some of our intuitions, and of course there are other reasons, but I'll tell you one of the more evocative ones, that the same physical pain is felt more sharply if you're of lower SES. The mind magnifies the physical pain. Very reasonable. And there are other less access to medication, different coping strategy, less social support. So we can give a lot of these things. I think I will put all of these into a hypothesis that I will describe as outside their knees, which is how I think I and many people think about this, which is that there are non-knee related factors that the same knee problem results in more pain in some groups. But here's another hypothesis. What if the problem is not something outside the knee of the patient and something in their heads? What if the problem is something that's not in the heads of the clinician looking at those X-rays? What if it's simply the case that, as Marzyeh mentioned in her talk, where did this clinical knowledge come from in the first place? It's from data, I guess. But we know that data doesn't completely represent lower SES people. So what if the problem is the clinical knowledge we have underrepresents the ailments of the poor? So how would we test this hypothesis? So to test this hypothesis, what we did is we've got this data set it's actually a beautiful data set because unlike most data sets that come from operating health systems where you might get one read by one clinician, this is a data set expressly put together to understand osteoarthritis. It has a set of X-rays. Patients are followed up consistently. It's a very clean data set. We've got all their X-rays. We also have their MRIs, but we're not using that in this. And we get the judgment of severity is not some clinician. It is sort of a consensus judgment where several people look at it. So it's kind of a good, clean judgment. of what the current state of medical practice leads us to believe. But we took that same data and said, okay, here's the x-ray, here's the clinician judgment. What if instead of the clinician judgment, I simply trained an algorithm to predict pain from the x-ray? The key here is the algorithm only sees the x-rays. It is not told the SES of the patient. So what do we find? First, and I'll go through these fast, the numbers here are somewhat less important, but if people are interested, I can stop and slow down. But it turns out the algorithm does predict pain better than just the clinician judgment alone, so that it's picking up some signal. But importantly, if instead of ranking people by the KL grade, clinician judgment, we rank them by the algorithm's prediction of pain, it significantly narrows the pain gap. In the case of race, it's completely gone. So you remember this figure, KL grade, blacks at the same level, algorithmic judgment, no difference at all. So what you see here is a slightly different story than the previous story, but we'll try and bring it back together. As an aside, this is not due to the algorithm simply reconstructing race or SES. It is finding something in the image. It is not simply finding a backdoor way. It's not due to discretization problems in the KL grade. The KL grade is 5 scores, ours is continuous. And it's not simply learning image artifacts. It's discovering something more fundamental about the need. Finally, another fact, which I'll just tell you about, is that our pain predictor also ends up predicting progression because we've got years of data. So when we get people who the algorithm says, wow, I see something in this knee that's problematic, the patient agrees with us. And the clinician says, no, it's low KL grade. There's no problem. It's in your head and also in the algorithm's head. If you go forward 2 years, that person, the clinician, ends up saying, oh, wow, the KL grade does look worse now. So in some sense, when the patient and the algorithm disagree with the doctor eventually comes to see it their way, which gives you a telltale sign or something going on. So finally, as just an observation, using the pain predictor to allocate surgeries would lead to more treatment for low SES because it's obviously finding that. So why did this happen? I think one hypothesis that's just so clear is that clinical knowledge is also empirically derived. As much as we think about algorithms using training data, the scientific community is using training data to train their minds. Humans are using training data to train. And that training data, well, who's left out in clinical trials? What have we tended to look at? What will we look at? And so there is, I think that's part of what's going on here. Let me just conclude by saying this, which is, I think these two things are emblematic of things that we're starting to find in a bunch of the healthcare work. I will emphasize a sort of somewhat trite, but also sometimes overlooked point, which is, as you saw in the first case, failures in algorithm design can magnify biases. As you saw in the second case, well-designed algorithms can dampen our biases. And there's just no good or bad here. It's just we've got something. The second point I want to end on is to say design is not about algorithm construction once the problem is posed. Yes, there are issues once we've posed the problem about how best to manage and build an algorithm. But to see this most clearly, if I simply took the machine learning applied, computer vision applied to healthcare playbook, you know what people would have done with that osteoarthritis initiative data? It's what people are doing right now. What will I have trained on? I would have trained on the KL grade. And then I would have simply baked back in the bias. And what would that paper have been looking like? The abstract of that paper would have read, much like in the first thing, oh, we use an algorithm to discover severity. Severity, what a funny word. It's not that. We use the algorithm to automate current human understanding of severity. It's not the same thing. It's kind of when it's spelt out at that level of tediousness, it shows there's something important. So as a result, I want to just end by saying, I think one source of bias, error, social problems that may arise is the problem construction. And if you think about it, I think in the world of expertise, this is the interstitial space where something is falling through. And here's why. On the one hand, you must be live and understanding all the things machine learning algorithms actually do and can't do and fail at and are prone to and so on. So you must understand enough of what happens once the problem is posed. At the same time, you must understand enough about arthritis and about this domain to be able to say, oh, I see where the problems are. And so I think one of the challenges we face, and a very real challenge in both of these problems, is who owns problem construction? Who is expert at problem construction? If you put two groups in the same side, an algorithm team who understands algorithms and a hospital chain that understands healthcare, oh wait, that is what happened in the first one. So it can't be that. There is genuine expertise, I think, that sits at this level. And I don't think we've only started to scratch the surface of that expertise and what that would look like. So, thank you.
And Dorothy Roberts.
I sent you my slides, but too late probably, so I have it on here, but I need a laptop.
No problem.
That's fine, yeah.
Yeah, I can imagine. That's
Oh,
my,
that's somebody
that's
else?
my
Oh, I see.
There we go.
No, it's okay. I can just push that. I'll just push that. Okay, great. Hi, everybody.
This is Dorothy.
Oh, yeah, Dorothy Roberts. Okay. So what I want to focus on is the question for our panel about race and health inequities, and I'm seeing all these people now that I'm up here, and in particular the problem of prediction. And I think it's very gratifying to me that my talk is going to touch on everything everybody else said. Some piece of it is incorporated here. You may have noticed, if you were following all the different notices of this workshop, that I switched among 3 different panels. I was at one point on carcerality, at one point on public policy, and unfortunately, because I can't be here tomorrow, I was switched onto this panel. But my questions are pretty much the same for all of them because of my particular interest in prediction and its importance in these issues we're discussing, and also the way in which prediction is at the core of injustices in predictive analytics and big data and automated decision making. So the questions I'm asking are, how can we end prediction as a way of foreclosing social change? So the problem I see with a lot of predictive analytics is that they're based on data that incorporates past injustices. And so what the algorithms do is produce replications of the past. So my question is, how can we then design technological models, like was just asked in the last panel, that instead of incorporating these assumptions and facts of the past that embed structural inequality, we use the models, design the models to be able to envision a different reality that is more equitable, humane, and just. And so can we use forecasting technologies then to envision a future that doesn't replicate the past? So if I were on the carcerality panel, I would have emphasized the way in which certain kinds of law enforcement technologies that prosecutors and judges and police are using incorporate data that already has racial profiling, for example, in it, and therefore end up reinforcing the past biases in policing into future policing practices or future predictions of who's going to commit a crime. And race, of course, is very much involved in all of that. But since I'm on this panel, I want to focus on the way in which the biological concept of race itself is a tool, predictive tool that incorporates past injustices. And what do we do about that? What do we do about the way in which race is so embedded in healthcare technologies and even the very practice of medicine, so that we can move to a way of using algorithms, and some of the panelists gave examples of that reject the assumptions about race that unjust medicine has been based on for centuries, and allow us to figure out better ways of dealing with health that create a more equitable society for everybody. Okay, so I want to just give some information about how race is used in medicine as a predictive tool. Some years ago, Sally Seitel wrote an article that was the cover article for the New York Times Magazine, where she said, "I'm a racially profiling doctor," and as many conservatives like to do, they make it sound as if they're saying something bold and brave, but actually, she says, "Illness isn't colorblind, so why is it taboo for doctors to take note of a patient's race?" Well, of course, it isn't taboo. Medical students are all taught that they should. The first thing they should do is take account of a patient's race, and then proceed to interpret the patient's symptoms and treat the patient, prescribe medication according to race, based on the assumption that human beings are naturally divided into biological races, and therefore their bodies function differently depending on race. This is so common that is embedded in medical technology in a way that is outside the individual doctor's hands. Although I don't understand why doctors don't rise up and say, "This is absurd, why are you giving us these kinds of results based on race?" But an example is glomerular filtration rate, which is routinely reported by race. So the amount of the protein in the patient's blood that predicts for kidney function and tells the doctor whether they should be concerned about kidney failure in the patient is automatically, categorically different for Black patients versus non-Black patients. Or I should say, at non-African American patients. I'm not sure what they mean by these categories in the first place. But in other words, the technology assumes that Black people's bodies work differently than all other human beings' bodies. We should all be gasping, right? But this is a current way that this test for kidney function is presented to doctors. Well, this is based on the biological concept of race, which a couple of the panelists talked about already, which itself is a predictive classification system. So the whole purpose of dividing human beings into biological races is to put them in a hierarchy that predicts their character and behavior based on assumed innate traits. It is a predictive biological classification system. Of course, as others have pointed out, it is an invented classification system that pretends that there are these biological differences, But the reason it functions so well to preserve white supremacy is because of this false assumption that it's embedded in nature and not in social or inequality of power imposition. So for example, Thomas Jefferson used the idea of natural biological distinctions to justify enslavement, and after emancipation, he said even then black people couldn't participate in democracy, a way in which to explain why there could be slavery in America at the very same time that he and others were promoting the view that America was a land of equality and the pursuit of happiness and liberty. Now, this idea that human beings are naturally divided into races that predict their character and behavior, and therefore that natural classification is the cause of racial inequality, is also long embedded in medical practice based on the racial concept of disease, that people of different races have different diseases and experience common diseases differently. This is an idea that still is a bedrock of the practice of medicine in the United States today. But again, we can see that it was developed in order to justify slavery. Samuel Cartwright, for example, proposed that black people had lower lung capacity than white people and had to be forced to work in order to be healthy. And the spirometer, which he helped to perfect, is another example of a predictive technology in medicine that automatically corrects in some versions of it. But there are lots of, these are just a few examples. There are lots and lots of technologies that automatically correct for assumed racial differences in bodily functions. Now, I could go on and on about all the harms that this causes in medical practice, but I'll point to just one which you mentioned, which is the well-documented undertreatment of black people for pain. And some of the studies have pointed out that even when black patients, describe their pain as severe, or when it obviously is severe, like little children being admitted in the emergency room for appendicitis in severe pain, black patients are routinely given less pain medication or no pain medication compared to white patients. And a recent study out of University of Virginia showed that the reason for this was that medical residents and presumably doctors as well hold these ideas about biological difference among people of different races. And so they found that a substantial number of white medical students and residents believe things like black people have thicker skin than other human beings, and so do not feel pain as much. Black people have less sensitive nerve endings. And the researchers found that these false beliefs predicted a mistreatment of black patients for pain.
What about dentists? What happens with dentists?
Dentists, I haven't seen, it's too painful to think about, but I can imagine that. I can tell you that when you say that, it brings back a memory of taking my children to a dentist in a white dentist in a black neighborhood years ago, where he had a restraint in a restraining a jacket hanging in, and I left immediately. But my thought then was, what is he doing to the children that he's treating in this place? Okay, so as Joan Fujimura pointed out, there has been a resurgence of the biological concept of race in genomic research and in epidemiological research, other kinds of biomedical research, since the mapping of the human genome, where these ideas about biological race are being refurbished with advanced algorithms and big data in order to create this idea that race can be proven to be a natural grouping of human beings. And also, as Nicholas Wade pointed out in the New York Times, a way to look for genetic differences between human races. And usually the justification for this is to improve health, because this will assist researchers in understanding health inequities as being produced by innate differences among different racial groups. And one study by Peter Chow White and Sandy Green, published in 2013, found that there actually was a spike in genomic research on race and genetics using race as a biological category as opposed to as a social construction. Again, race being described by many genomic researchers today as a population that can be inferred from genotype data based on statistical probability. So race itself as a statistical grouping that then predicts, supposedly, outcomes, including health outcomes. So in other words, race is itself a predictive risk factor that can be used in algorithms and other ways of predicting health. One example of the use of race itself, independent of all social factors, as a predictive variable for a negative health outcome is this hypothesis that Black race, independent of other factors, increases the risk of extreme preterm birth and its frequency of recurrence, which got a headline in the New York Times saying that this study pointed to genetic differences between races as being the cause of higher rates of preterm births among Black women. Now, as Nancy Krieger pointed out, this view has been challenged by research that is looking at the way in which structural racism, not race, produces these inequitable outcomes. And I just want to point out that this is a long-standing debate within health inequity research that even Du Bois, 100 years ago, was arguing that the dominant view, which remains the dominant view, I think, that it is innate differences that produce health inequities, is wrong, and that it is actually the conditions produced by structural racism, by political inequality, that causes these disparities in health. So racism, not race, as the risk factor that should be used in scientific research to explain and end health inequities. Just one example of such research is this study published in 2014 that looked at the impact of living in states with high levels of structural racism. I think Nancy Krieger gave some examples as well from her work of similar kinds of research looking at the effects of racism as opposed to the assumed natural products of innate biological differences. So in conclusion, I think it's important to remember that race is the product of racism. Racism is what produced the invention of the false assumption, the false claim that human beings are naturally divided into races that predict not only health outcomes, but supposedly also predict their fate in society. As I say that, you can see that's also the basic thinking of eugenics, which in another talk we could look at the relationship between eugenics and statistical risk. But the same idea that it is some innate difference among human beings that produce social inequality, that false belief is based on a view that race is natural, or with respect to racism, race is natural, and that then produces racism because of a supposed human propensity to hate people of other races or to be biased against people of other races, when in fact racism came first, and that is the only reason to have a theory, a made-up theory of human beings as naturally divided into races. I think this, to me, helps to clarify what the risk factor should be in algorithms that are trying to improve health. If you understand the relationship between race and racism. And so in conclusion, in answer to the questions that I asked at the beginning, or partial answer to it, yes, like Joan, I don't have the solutions, but one important lesson I think that we should keep in mind is that in terms of the relationship between prediction and health equity or health inequity, it is structural racism, not race, that is the risk that our technological design should engage with in order to help us to envision an equitable future that doesn't replicate the past. Thanks.
So I could not have predicted that alphabetical order would arrange that discussion and summarize so beautifully and perfectly. We'll have a short break and then come back for questions and discussion. Let's say, the schedule policy. Great, our break is over. Come back in 10 minutes.